Okay, 1.5. So first touch on these things. I want to give you notes. We're going some terms you need to know. Okay, before we get into this. So let's just say, yep. See, it'll only be one note, but it's a little bit to it. Okay, so let's try to do this quickly if we can. Let's go over this page before we get started. Make sure we're on the same page here. So, segment bisector is a term we need to know. Segment is just a line that starts and ends somewhere, right? Not the full line. Good. So to bisect something needs to split it exactly in two, right? So a segment bisector divides a segment into two congruent segments, okay? Divides a segment into two, and there's our congruent symbol. It's an equal sign with a squiggly over it. That means the word congruent, right? Everybody got that now? We use that a lot. Into two congruent segments. Okay? And it goes through the segment at its midpoint. So it goes through the midpoint. I'll draw a quick little sketch here. So there's a segment with a couple of endpoints. We'll call this segment AB, line segment AB. And let's say that's the midpoint. We'll call that M. That line I just drew is called the segment bisector, okay? And that makes this segment here, AM, congruent to segment BM. Those little marks I just made are congruent marks for segments, okay? You've seen those before? Okay. So we can say that segment AM, that's the bisector, AM, and that's a symbol for line segment, the little line above it, okay, is congruent to segment BM, if that's a segment bisector, okay? We got that? Now, do we know what perpendicular means? Well, perpendicular means the two lines that intersect at right angles. I've heard that before, right? Means intersecting. Well, what's a right angle? Yeah. At a right angle. 90 degrees. Okay? And we have a symbol for perpendicular we can use to write the word perpendicular. I'll put it in quotes. That symbol means perpendicular. We can use that instead of writing the whole word out. Okay? So a right angle would look like that. And this is the right angle mark somebody mentioned earlier, right? That means it's 90 degrees. Okay? Or if you have the two full lines, right? How many right angles are formed if they're perpendicular? All four of them, right? Okay. Well, now you know what a bisector is. You know what a perpendicular line is. What about a perpendicular bisector? Notice that this bisector I drew wasn't perpendicular. I did that deliberately, right? Because now we can talk about a perpendicular bisector. Perpendicular bisector. It's like a regular bisector, except, well, what do you think the difference is? It's perpendicular, right? So if that's A and that's B, there's a right angle, and they are congruent, perpendicular bisector. And that's going to be the first thing we want to construct, by the way, with compass and straight edge. It's the simplest one, it's most useful. We use it a million times, okay? Anybody ever heard the word vector? I don't mean it like in the movie Airplane. What's the vector, Victor? Okay. Oh, we got lunch, huh? Like,
I'm just cleaning.
oh, I thought you had a lunch cart with you there. I saw that earlier. Okay. So a vector is just a ray. A ray is like a one-directional array that starts and ends, okay? So it's a ray with an initial point, starting point, with an initial point, okay? And a terminal or ending point, okay? You guys know that terminal means end, right? To terminate something, or someone has a terminal disease, they're going to end, right? Okay. Array with an initial point and a terminal point. Okay. It has what we call magnitude or length. It has a certain length. Okay, it starts and stops somewhere. So it has magnitude, which is its length. And I know we're going pretty fast here. If I like scroll too fast, you don't get it, let me know. I know I'm standing in the way too, but just do our best. And direction. Okay? So it, as a diagram, it looks something maybe like this. Down here is the initial point A. And at the very tip of it, see, in this case, it's a vector. Usually you think that means it goes on forever. But if you know it's a vector, you know that this point at the tip is the ending point. It's a terminal point, B. Okay?
So we're taking another down.
No, it's already got the point. You can if you want. You really want to be focused. And the notation, remember we had segment AB up above with the segment symbol above it? Okay, these notations are important, right? Vector AB, the symbol for vector, is that like half the arrowhead on top, right? And that way you know it's not a line that goes on forever, right? Because line would have the arrows completely, right? That makes sense? So this is red. You read this as vector AB. Okay. And some of the notation we'll use. Now we use a certain type of brackets around it. Okay, you know how you have like parentheses x comma y, and it represents one point in the coordinate plane. Okay, it'll look a little like this, but don't confuse it. Okay, it's going to have the pointy brackets with some x value and a y value. It's not a single point, right? So for the notation of it, the way we'll use it. Right? It'll be some amount in the x direction from any starting point, right? Anywhere. We're not necessarily starting at 0, 0 in the plane, right? We could be starting at the point 5, comma 2, and then going over x or up and down y, okay? Like that. So if this is our vector starting anywhere, right? It starts here at the initial point. It has some x direction, right? And then also some what? Y direction. And generally those will be replacements unknown, okay? Which I'll give you right now. So if I tell you the vector is this, 4, comma 3, this vector in the coordinate plane can start anywhere you want it to in the coordinate plane, not just at 0, 0, right? So that would look like this, right? That x direction from where we started is going over 4 and what? Up 3. Does that look a little familiar, like one of our transformations that went over 4 and up 3? What's transformation? The translations, right? Left, right, up and down. So this actually can replace the mapping notation that we used before, right? So if I see this vector, it actually can replace, so it replaces in certain context, this rule. This here replaces this rule. XY maps to x, parentheses, plus 4, comma, y plus 3, right? So you can see that this right here will do the same thing to your figure as this will. You can think of this vector as pushing the figure around, right? You apply it to all points, okay? And this is for a translation. If you're a little confused, you'll see how it works. All right? Oh, we're gonna get this in? Let's get as far as we can, and then we can pick it up. If we don't, I'd love to. All right, everybody have that? Can we go back? I don't want to go too fast, but I want to right. 11:15, we're done. Eventually, it's supposed to be 1 o'clock, then 11:30. Now it's 11:15. 10 minutes. Mr. Miller, it's true we're done at 11:15. Is that true? Is that right? Sweet. Okay. Let's talk a little bit about reflections here. So there's some real fine details we need to know about reflections, some of these other ones, right? So you have a line of reflection, right? Are you with me on that? Okay. So when we reflect over that line, the distance from, say, A to that line is the same distance as A prime back to the line. And every single point is the same distance from the line as its image on the other side. Does that make sense? So all of these distances on either side of the reflection line are the same for reflection, okay? Now, this line of reflection, like if we take this path from A to A prime and call that a line segment, that line of reflection is the perpendicular bisector of the segment joining those 2 points. Remember what, because I just gave you a note on perpendicular bisector, right? So this path from A to A prime, that is a perpendicular, boom, bisector. And these are the congruent marks. Does that make sense? And these would also be, and notice how they use for these a single congruent mark, which tells you, all right, these two are the same, but not the same as these two, but they're not the same as these with a triple congruent mark. Does that make sense? Okay, all right, good. So our notation for a reflection looks like this right here. It's a lowercase r, and this subscript right here, if you write it, it's got to be a subscript, not just RM. R, a little tiny m down to this foot, okay? It's called a subscript. So this M is the reflection line. Right? As you can see that reflection line, they've called it line M, right? Sometimes it's going to be, you know, the line x equals 2. So it will be R subscript x equals 2. Or the y-axis, so it will be little r subscript y-axis. Okay? Just to tell you what the reflection line is. In this case, triangle ABC gives you A prime, B prime, C prime. Okay? Now, let's talk about orientation. Okay? Because reflections are the only one that does what we say reverses orientation. Okay? So let's say I read ABC around, I'm reading it A to B in what direction, and a B to C, what direction am I going? Clockwise or counterclockwise as I read around? Clockwise. But after the reflection, now I go from A prime to B prime, which way am I going? Counter. That's the orientation, okay? Now I'm reading the lettering counterclockwise. So a reflection reverses orientation, okay? So a reflection reverses orientation. Because there's going to be times where, oh, it's hard to tell what this was this a reflection or did they rotate it, right? And if you want to know for sure, take a look at the orientation. Are you reading the letters around the opposite way the original one? If you did, it's a reflection. If not, it's probably a rotation. That makes sense? Okay. Yeah, we're not going to get through all this. So let's look at some properties here. So reflection line was isometric. What's another word for isometric? Yeah, or rigid, remember? Yep, same sign, same say, rigid. They're interchangeable, okay? So a couple cases here. If I have a reflection line and the point I'm reflecting is not on the line, okay? So point P gets reflected, if it's not on the line, then line M, the reflection line, is the perpendicular bisector of that segment. See that segment name with the segment above it? PP prime. Just like I showed you up there, right? So it's perpendicular and they're congruent. Okay? Even if let's say I had another point here. Let's call this point B. And I reflected that as well. Call that B prime. Okay, well, this is perpendicular, isn't it? And these guys are congruent to one another, okay? Which means, like, if I had this segment here, now I could say it reflected a whole segment, and it came over here to the other side, see what I mean? Okay, so that line of reflection is the perpendicular bisector of the path of each point. Okay. But what if point P that you're reflecting is on the line? What if the point you're trying to reflect is actually on the reflection line? Where does it move to?
Nowhere.
It doesn't go anywhere. When you look in the mirror, right, and you press your nose right against the mirror, where's the reflection of your nose? Right on it. It's at the same place. So your nose and its reflection are basically equal to each other, right? So if P is on the line, then P is equal to P prime. See how they have that there? Okay? So let's fill in some of these real quick, and then probably just finish this up, and I guess we'll be done. And I'm not recording. Oh,
Yes, you are.
am I?
Yeah.
Oh, I just got that all. With my little helpers, I'll go back in and edit that.
Why? Just leave it in.
Okay. At least it didn't curse or anything. All right. So, how about the distances from the pre-image to the image? What can we say about this? So, like this point P, its distance to the line, and now how about from point P to point P prime? Compare the distance between P and P prime to the distance between P and the reflection line. What could you say about it? Okay, so that means that the whole distance is what compared to this original distance from the line? Twice, right? Yeah, there we go. We got it. Okay. So twice the distance from the line. Twice the distance to the line. That's what I meant to say. So it's twice the distance to the line. Okay. Oh, and by the way, real quick, also, this path that B takes to B prime and P takes to P prime, could you also say that they're parallel to one another? Yeah, because that's going to be important later on too. Now, what do you think that the reflection does to the orientation of the figure? What do we say? Reverses it, right? In the segment, it's kind of hard to see that, but it, triangle are bigger, right? So it reverses it. And special points, like points that are on the line. What happens to them? So if a point is on the reflection line, it maps where? Onto itself, yeah. Well, even more than just the same area, it maps directly onto itself, right? So points on reflection line map to themselves. Okay? So in other words, that point P maps to itself, and it becomes P prime. There we say. All right, so we'll have to pause it there because we'll pick up the rotations tomorrow when you first get in there. So I can't really assign you a problem set for this. Huh?